Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
For once, I'll be talking about two recent papers, both of which I did with my two advisors, Daron Asemoglu from MIT Econ and Assos Daglar from MIT Electrical Engineering. And the title is Optimal Pricing in Networks with Externalities. And networks here means social networks, okay? So as a way of motivating the talk, I would just say that social networks are instrumental in the propagation of information. They act as conduits of influence among agents. They're instrumental when we want to find out about a new product, or we want to find out which team to bet on in Champions League. And nowadays there is plenty of data available that kind of describes at some level the pattern of interaction among individuals. And the question we want to address here is whether and how can businesses exploit this data to make better decisions. Okay? This talk consists of two parts. The first one will be about a pricing problem. We will consider a network good, okay? A good that exhibits positive network externalities. And the question I would like to address there is, how should the monopolist price such a good to better exploit the network? And in the second part of the talk, I'll briefly describe a model of how information might propagate in a network, okay? So to motivate the first part of the talk, I'll start with a somewhat unrealistic example, all right? Suppose that tomorrow Facebook started pricing the service, okay? So I derive utility by being a member of the Facebook community. However, this utility is larger the more my friends are part of the Facebook community, right? So the question I want to address here is, how can Facebook actually exploit this fact to increase its revenue, okay? Abstractly, the problem looks as follows. There is a two-stage, it can be described as a two-stage game. In the first stage, the monopolist chooses prices, and in the second stage, the agents observe those prices and make their consumption decisions, okay? And the question is, how should the monopolist choose those prices so as to optimize her revenue, okay? All right, so the agent's utility can be thought of a three-term function. The first term is simply how much utility I derive only because of my own consumption, and this has nothing to do with the network. The second term is the utility I'm deriving by being part of a community, and here G describes the level of interaction with my peers, okay? How much I care about others. And finally, the third term is the cost of buying Xi amount of the resource, okay? So the question I want to address in this setting is, when is price discrimination beneficial for the monopolist? How do the optimal prices relate to the network structure? And what is the revenue loss when one ignores those externalities, okay? All right. So to put our work into some context, there is plenty of previous work on network externalities. I'm just putting here two seminal papers by Kachin Shapiro and Farrell and Saloner. There, the externalities are of global nature. So I'm simply interested in the market size of the good. In our case, the externalities are local. Okay, I care about my neighborhood. I don't really care about how successful Facebook is. There is also some recent work on so-called network games. These are typically one-stage games, and the questions that they address is about identifying properties of the equilibria, and not so much about how can anyone exploit the fact that there is some network. And finally, there is some work in the computer science literature that deals with problems of similar nature. However, there the questions are mostly algorithmic, and there is no qualitative insights on how prices, say, relate to network structure, which is actually the focus of our work. Okay? All right. Okay, so to make things concrete, this is the utility function we are working with. So the first two terms represent the utility I derive from consuming xi amount of the resource. The third term describes the utility from the network. Here, xj is the consumption of agent j. Gij represents how much I care about agent j, right? And finally, the last term is simply the cost of using xi amount of the resource, okay? We make our lives easier by assuming such a utility function. The main thing that this buys us is that best replies are linear. This is somewhat essential for tractability of the problem, and we believe that this is a good assumption for the general class of concave utilities. Okay. So now the monopolist problem. Yeah.
Is there maybe some intuitive interpretation? Why would you take the product cross product xij? So basically, product of consumptions to be somehow measurable.
So I mean, we are taking the product because I care more about others the more I consume the good. That's what this tries to model, right? So it could be xi could we could just omit xi from there, but then no matter how much I use the good, I would care the same about how much agent j use the good, which is, I don't know if it's a good assumption.
It makes sense in the binary setting where you join or not join.
Exactly. So that's a good explanation too. Okay. So here's the monopolist problem. The monopolist picks prices, PIs are the prices, and tries to maximize her revenue, subject to the constraint that in the second stage, the agents will pick xi so as to maximize their utility. So this is an equilibrium constraint, and it's derived from the second stage of the game. Okay, and we have a bunch of assumptions here. The quadratic term in the utility function dominates. Otherwise, eventually dominates. Otherwise, an equilibrium would be everybody consuming infinite amounts of the resource. And the second one is not crucial. We use it for simplicity. It simply says that for every agent I, there is a price that the monopolist can charge that agent, so that the monopolist forces the agent to buy a positive amount of the resource, and does so profitably. Okay.
So there is Nash equilibria because it's a concave game.
Right.
Okay. And there is a uniqueness.
This guarantees uniqueness. Okay. And this guarantees that it's not it's in the interior. It's not on the boundary. Okay. Okay. So first setting, the monopolist can perfectly price discriminate. I can pick a single price for each individual. So this might sound a bit unrealistic, but you can kind of implement it by offering promotions, right, that are targeted to specific individuals. Okay. The results we get here, the result we get here is that the optimal prices look like this. there is the first term here is a nominal price that has nothing to do with the network. The second term is a markup that the monopolist charges agents because of the utility they derive from the network. And the third term is a discount that the monopolist applies to the agents because of the utility they offer to the network, right? So interestingly, both of those terms are proportional to the so-called Bonacci centrality of the agents, okay? And if you see, they're identical except the fact that here we have G and there we have G transpose, okay? It's like how much mass is leaving out of the agent versus how much mass is coming in, okay? And all right, so this is intuitively proving what you would expect, that the monopolist wants to favor central agents, okay, by offering them deep discounts. And the nice byproduct we get is that this Bonacci centrality is a very well-established sociological measure of influence, okay? And now we put this and prove that it actually is the outcome of some economic model, okay? It's the solution of some economic model. And we find that this is a nice byproduct of the analysis.
So what kind of function is that?
This,
yeah,
I should have said here that the Bonacci centrality is very similar to the PageRank, of agent I. So if you think of a network and of the network and running a random walk, okay, then it's pretty much the stationary distribution of the node. Okay, that's what sociologists call Bonacci centrality. That's what is also called PageRank vector, and we prove that this is actually proportional. This has to do with the optimal pricing problem of the monopolist. Okay, all right. So now the second setting we study is what if I can only choose one price, right? I cannot perfectly price discriminate, but I can only choose one price. What should that price be? Okay. You can think of this price being too high, so some individuals will not buy at all because this is too expensive for them, but the monopolist will extract the lost revenue from the others. Okay. A lemma here that helps us with the analysis is that if we knew, or actually if we restricted attention to a subset of the agents and required that those agents should buy a positive amount of the good, so we would ask the monopolist to offer such a price so that at least those agents buy a positive amount of the good, then we could solve for the optimal such price and for the revenues in closed form. Okay, so this kind of suggests a naive algorithm for solving the problem. Take all possible subsets, compute the optimal prices for each such subset, and finally choose the price that maximizes your revenue. Okay, but we can do better. Okay, we can come up with a greedy algorithm that exploits the so-called centrality index of the agents and do the same thing in polynomial time. And the algorithm pretty much does the following. We start with the set of active agents being all agents, okay? And as we increase the prices, we drop the agents with the lowest centrality indices. And you can show that once you drop an agent, it's never optimal to bring him back, okay?
So what exactly is centrality here?
So this has, it's very similar to what I called R in the previous slides. So when all n agents are considered, it's simply the page rank of the agent. Once you drop that agent, you have to recompute it. Okay. All right. And finally, and probably more realistically, what happens when I can offer two prices, right? So I have a full price and a discounted price. And who gets the discounts? Okay. Obviously, the problem should be NP hard, and it is. And intuitively, it should be clear that it looks like a max cut pretty much. So you have to partition the agents in two subsets. One gets the discounts, the other does not. And you have to pretty much maximize the influence that goes from one subset to the other. And this kind of gives the intuition for the proof. And since we use the reduction from max cut, we can exploit some nice properties of the max cut problem to come up with a good approximation algorithm. So we use similar techniques as Goemans and Williamson, the randomized approximation techniques, and we come up with an approximation algorithm that achieves around 90% of the optimal revenue under some mild conditions. Okay. All right. Okay. So far I've been dealing with the problem of finding the optimal prices, and a complementary question would be, when does the monopolist make most of her information on the network structure? When does the monopolist have to invest in finding out what the underlying network looks like? Okay? And to answer this question, we compare two extreme settings. The first setting is one in which the monopolist prices as if there is no network. Okay? However, the agents decide, given their knowledge of their network structure. That's one setting. And the second setting is the one that the monopolist knows the network and can perfectly price discriminate. And what we are interested in is in seeing how big this gap is. Okay? Obviously, the monopolist will make more money here than here, but the question is how much more. Okay? Okay. So this lemma simply characterizes the profits in the two settings in closed form. And the main result in this section is actually providing both a lower and an upper bound on this ratio, on the ratio of the two profits, that pretty much depends on the minimum and the maximum eigenvalue of a matrix that is related to the interaction matrix of the agents. Okay? And I'll show you some pictures that clarify this point. A good corollary here is that when the interaction is symmetric, meaning that agent I influences agent J, and in the same way agent J influences agent I, then there is no need to know the network. The revenue that you can make either knowing or not knowing the network is the same. Okay? This is, I should say here that this is specific to the utility function we chose. Okay? The fact that you can not increase your revenue by knowing the network. However, what is robust in the selection of utility functions is that the more symmetric the network is, the less I care about the network. Okay? So you can exploit the network structure if the network is asymmetric. And this is a robust finding. It doesn't depend on the utility function. So here are some pictures. What we did was we simulated, we did some simulations for specific families of graphs. First of all, star networks. Stars are, the way we define stars is the following. We have a special agent, say agent 1, and all influence goes outwards from 1 or inwards. Okay? These are the two extremes. G1 is the one that all influence goes outwards, and G2 is the transpose, where all influence goes inwards. Okay, and we run our simulations for a convex combination of these two matrices. Okay, so of these two extremes, and here's what we get. The ratio of the two profits is larger at the extremes. Okay, the more asymmetric the network is, and it's actually 1. Sorry, so there is no loss by not knowing the network when alpha is a half, meaning that the interaction matrix is symmetric. Okay, and here we see that not knowing the network, in the extremes we lose 25% of the optimal revenue for some values of the parameters. For some other values we lose a lot. We lose 90% of the revenue, 95% of the revenue. So, but this is specific to star networks that can be thought as the most asymmetric graphs that one can get. We run the same.
Sorry, what were the two graphs?
So these are for different parameters. Choices of the other parameters, the alphas and the betas. Okay.
So alpha is the x-axis.
Mm-hmm. Okay, so we run the same for general matrices. We get an upper triangular matrix, and we do the same experiment. We get similar pictures, and finally we do the same for preferential attachment networks, and we again show that by not exploiting the fact that there is a network structure, the monopolist loses something like 30% of her revenue in the worst cases. Okay. All right. So this summarizes the first part of the talk. What I described is a model of pricing for a divisible good when there are strong local positive effects, and the model highlighted the benefits of accounting for the underlying network structure. Future directions include doing the same thing in a competitive environment. Suppose now you have two firms competing over consumers, and the good that they're offering exhibits strong network externalities. Okay? How does the intensity of the competition between the firms depend on actual network properties of the consumers? And another interesting direction is combining this framework with social learning. Okay? What do I mean by that? Suppose that a new product is introduced in the market, and the product has unknown quality. The only way that a consumer learns about the quality of the new product is by experimenting with it, by buying and experiencing the product. Okay? And you can imagine that the more people buy, word of mouth kicks in, and the product becomes more attractive for the rest. Okay? And suppose now the monopolist has a few promotions to give. How should the monopolist target those promotions so that to maximize the word of mouth effect? Okay? Before doing so, though, we need a model that actually describes how information propagates in a network. And the second part of the talk is a way of doing that. Okay? All right. So what is our formulation in this problem? We have an unknown state of the world. So this unknown state of the world captures the unknown product quality or the unknown competency, say, of a political candidate. And the dynamics of information are captured by the beliefs of individuals about this state. Okay? These beliefs evolve based on private and public information that gets available to the agents. And the individuals take actions whose payoffs are conditional on the state. And the timing of the action is endogenous, meaning that agents not only choose which action to take, but also when to take that action. Okay? And the questions we ask in this framework is, what is the role of the network structure in the evolution of beliefs? Under what conditions do the dynamics that I'll describe briefly lead to the efficient aggregation of information? Who are the central agents in this process? The major challenge we are facing is that agents strategically interact with one another. And to make everything clear, here is a simple illustration. Suppose that so agent 1 wants to decide whether to go for summer vacation to Greece or Italy, right? And say agent 1 is American, so he has no idea about what Greece or Italy is, okay? So, all right, so but agent 1 lives in a social network, right? And he can potentially obtain information from his network. Suppose at the beginning everybody has an opinion, right? That is based on some partial information on which of the two places is better, okay? So at t equals to 0, agent 1 just knows his prior, he prefers Greece if he doesn't obtain any information from his peers. In one time period, he gets to know what his immediate neighbors think, okay? What his immediate neighbors know. So by this new information, he updates his beliefs. So now there are 4 signals favoring Greece. There's just one favoring Italy. In the meantime, agent 2 has had enough with this discussion and decides to go to Greece. So takes an action. And what this implies for the information aggregation process of 1 is that the information that one could potentially obtain from agents 9 and 10 is lost, because agent 2 has taken a decision, and we assume that he has no longer an incentive to continue searching for information. So he can communicate all the information he had at the time of his decision, which is the information of agent 8, but not any more information other than what 8 thinks. Okay? So in particular, this is a central feature of the model, which says that although we start with a fixed and given network, the actions of individuals, so the fact that agent 2 chose to go to Greece, change the network topology and may break information paths. Okay? All right. So, and the information process continues, and obviously agent 1 goes to Greece. Okay? All right. So there are many approaches in studying information aggregation and propagation in networks. The most prevalent one would be that of aggregative models, which consider the market at an aggregate level. And they do not really look at individual incentives or local network effects. Okay? There's another line of literature which is very popular in the CS community that treats information as a disease. Okay? So the fact that I know something means that you will know it with probability P. Okay? And this is a good first order approximation, but doesn't really model incentives of individuals and treats individuals as black boxes. Okay? And finally, there is a recent line of work on microeconomic models of information propagation. Individuals are considered to be rational. They have a utility function, and they take actions that to maximize this utility. Okay. All right. So here is our model in more detail. There are 2 states of the world. Okay. Whether Greece or Italy is a better vacation spot. and there is a fixed and given communication network. We study network formation, but I won't talk about that in this talk. Each agent receives a signal that is correlated with the underlying state. You can think of the signal as the coin flip of a biased coin. Okay? With 60% it gives the correct state, with 40% it gives the opposite. Okay? Agents receive information through their neighbors, and at each time period they can choose to take an action, which is guessing what the state is, or choose to wait to obtain more information from their network. And here is the payoffs. So if the agent chooses the right state, he gets a payoff of pi, discounted by the number of time periods it took the agent to actually decide to take the correct action. So there is a clear trade-off between waiting and taking an action. The more you wait, the more information you get, and the better action you will take, the better informed action you will take. However, payoffs are discounted, so you cannot wait forever. Okay? We make a few assumptions. The first, we assume that individuals have the same discount factor, have the same signal precision, and they have the same preferences. Okay, they all prefer to go to Greece versus Italy if they had complete information over everything. Okay, the only source of heterogeneity among the agents is where are they located. Okay, there are no payoff externalities. The fact that I go to Greece doesn't make Greece more attractive for anybody else. Okay. The only way our actions are tied together is through informational purposes. And finally, no information is obtained after an action is taken. This is a very crucial assumption, and it buys us a lot. Modeling the fact that after taking an action, an agent might become more informative actually for his social network is yet another line of work that has to do with experimentation and strategic issues. I'll touch upon that in the end of the talk. And the reason why we make all these assumptions is simply to focus on the exchange of information among agents and how the structure of the network affects their information aggregation. Okay. All right, so here is the decision problem that an agent faces. It can be cast as an optimal stopping problem, right? When is it optimal for me to stop communicating and take an action? However, unlike traditional optimal stopping problems, my decision depends on other people's decisions. So in particular here, if agent 1 knows that agent 2, 3, and 4 will not exit, will not take an action at the first time period, he might choose to wait as well, right? Because not only he will get access to their signals, but also the signals of their neighborhoods, okay? However, if 2, 3, and 4 exit immediately, then the incentives for agent 1 to stay are much lower, right? Because now, although he may have access to those 3 signals, he won't get access to those, okay? So my decision really depends on what others do, okay? Okay, so the information set for an agent at time t is simply my signal and what messages I've gotten from my neighbors up to that point, okay? And the strategy is a mapping from my information set to the set of actions, okay? And the equilibrium concept we adopt is that of perfect Bayesian equilibrium that simply states that at every time period I'll take the action that maximizes my expected utility given my information set and given what others are doing, okay? All right. We are interested in what we call learning, right? We consider a sequence of communication networks that grows. Okay, this is what we call society. N here represents the number of agents in the society. And we say that learning occurs if the fraction of agents that take the wrong action goes to 0 in probability, okay? So informally, we allow only a negligible fraction of the agents to take the wrong action as the society grows large. Yeah?
So what exactly are the conditions of based on the state communicated between two nodes? Somehow in a simple interpretation it was like the action selected. Could it be some more complete information about the current belief of a neighbor?
Okay. So the crude simplification of all this would be that at every time period I simply transmit to you whatever I know. Okay? So whatever I heard, all the signals I've heard. Okay? You can simply transmit a sufficient statistic of what I heard. Okay? So for example, in the case that signals are 0 1s, I can transmit to you how many more ones I've heard from zeros. Okay? However, what is important and what was not captured by earlier models is that I have to know how many of them, of those signals, I've heard before. Okay? So that I don't duplicate information. Okay? Okay. So the first result we get is simply a characterization of the optimal actions given my information set. Okay? Lambda here is the likelihood ratio. SI is the message, my signal, and this is all the messages I've gotten from my neighbors. Okay, so if this sum here that represents the information I currently have, okay, is smaller than a threshold that depends on the equilibrium, which means that this is what information I'm expected to get in the future from my neighbors. If this sum is smaller than the threshold, I take action 0. I think that 0 is more probable than 1, and also it doesn't buy me to wait more. If this sum is greater than another threshold, I take action 1. Otherwise, I wait, because the information I have is not conclusive on which of the two actions is better. Okay, and these thresholds we can compute. It's a simple DP. Okay. Now, what we are really interested in is, given that the society grows, under what conditions does what we call learning occur? Okay, which societies are better than others in terms of learning? And in this talk, all the results I'll state are in the asymptotic limit. We have some partial results for maybe more realistic assumptions, but I think this will be more clear if we stick to asymptotics. Okay, so the first step of the analysis is simply assume that the feature that made the model interesting in the first place, the fact that if I take an action, I exit, I leave the network, does not hold. So even if agents take an action, then they stick in the network, and then they can still transmit information. Okay? We use this as a first step in the analysis, and I'll show later on how one result maps to the other. Okay. So we define a minimum communication radius as the earliest time that an agent can take an action, okay, given any realization of the signals. In this case, if agent A gets all ones, he might decide that 1 should be the state at time t equals to 1 and exit. However, if he gets a different set of signals, he may choose to wait at t equals to 1. We are interested in the earliest time that agent A will exit, so we say that the minimum communication radius is 1. Okay? And similarly, we define k-radius sets, which have the following meaning. We say that agent A belongs to a k-radius set if the number of other agents in radius equal to his minimum communication radius is at most k. Okay. So the first result in this simple setting is that asymptotic learning occurs if there is only a negligible fraction of agents that have a small communication neighborhood. Okay, and this doesn't say much. I think a better illustration of this result would be through these special agent types. We say that an agent is an information maven if the log likelihood ratio of her information in one time step goes to infinity. If all agents have the same signal precision, this simply means that agent I has a large in degree. Okay? And we say that an agent is a social connector if the agent has a large out degree. Okay? Okay, the result intuitively says that the society needs to have at least one maven, so an agent that can aggregate information quickly, and almost everybody has to be close to that maven. And what we mean by close has to do with the discount factor, has to do with the thresholds that I showed before. Okay? Okay, so mavens are not enough for learning. Even if you have agents that know everything, this is not enough. You have to have also agents that transmit their information quickly. So the picture pretty much looks like that. The mavens aggregate the information, then the connectors pass this information to the rest. Okay? And of course, this sounds intuitive in the asymptotic limit, but same insights hold for epsilon asymptotic learning, where we are interested in guaranteeing that at least a fraction 1 minus epsilon of the population learns. Okay? Okay. So far I've been talking for a static environment where, as I said, agents, when take actions, do not leave the network. However, the same results hold for the dynamic environment, where when agents take actions, they destroy information paths. Okay? The intuition is given by this figure, and it goes simply as follows. Say that node I would communicate with maven L in the static environment that I explained before. Now, the only way that I will not communicate with L in this more dynamic environment is if J, a node that lies in between them, exits prematurely and breaks the path. Okay? But if I has an incentive to stay and communicate with L, then so will J. Okay? And of course, this is a simple argument. We need to take care of some extra stuff, but this is the basic idea. Okay. Okay. So this is something that this is an insight that that can be easily derived by this model, but it's quite counterintuitive. And the question we ask here is whether more information is better. Suppose we make the following experiment. We add a supernode that has a good signal precision, and we make his information available to everybody. And the question we ask is whether this helps society, whether this increases social welfare. Okay? The answer is more information is not always better. Okay? From one hand, more information means that I can make my decisions with better information. However, the fact that I have this information early on might reduce my incentives for search and might decrease the communication among the agents. So overall, the agents will end up having access to less information at the time of their action. Okay? So this motivates the following question. When does a group use this dispersed information efficiently? So compare equilibrium with a setting where a social planner would say you communicate with him and you stay for 3 time periods and so on and so forth. When would the social planner actually do better than equilibrium? And the answer here is that there is a direct connection between learning and efficient communication. When a society learns, then the social planner cannot outperform equilibrium. Okay? All right. So here is the summary of the talk. In this second part, I developed a microeconomic model of information exchange in networks, and I illustrated another dimension of strategic behavior. I might delay my actions not in anticipation of a better price in the future, but to get more information about something I don't know. Okay? And coming back to combining the two, suppose the two parts, suppose that the monopolist can change there is a monopolist that is interested in spreading the word for a new product and can change the precision of some signals. How should the monopolist target which individuals to change the signals? And finally, as I said, we have some results on network formation. The question there is, given that agents are interested in acquiring information, and given that forming links is costly, what shape do we expect equilibrium networks to have? Okay? And with that, I'll conclude, and thank you for your attention.
Any questions? Maybe I'll ask one. Oh, you go first.
No, for the first part of the talk, it would be interesting if you apply the model in kind of realistic social graphs. I mean, there have been, I think, a couple of groups that published, crawls of Facebook, crawls of Twitter, and things like that.
Yeah,
I guess it would be similar results, but just to.
Yeah. So what we were thinking of doing is apply that to Microsoft Ads. So the question there would be, say that I have some knowledge of the underlying social structure from MSN, okay? And I have also some data on how effective some ads were for particular agents, whether I can use this to infer how much these ads will be, how effective will these ads be for agents that are similar or close in the social graph with the ones I experimented with. Okay, but yeah, it's a pain to get access to the data and actually apply all this. Maybe if we get an intern that is interested in the summer, I'll do that. Yeah, I don't know. I don't think I have much incentive to do that myself.
So maybe a question like in the first part, okay, there was this profit comparison result, taking a natural benchmark, which is monopoly not knowing anything about the graph. So could there be some other benchmarks where maybe monopoly may have some partial information? So he doesn't know entirely G, but may know some.
Yeah. So
something.
yeah. So Another thing we could do is say the monopoly knows something about the degree distribution. So has some beliefs about how many people have that many friends, right? And try to or the monopoly has some partial information on which ones have the most friends. Okay, what the highest degree, what can be done then. Okay, what the first part tried to illustrate is that the degree is not the best descriptor of one's influence, right? So typically when you see papers that kind of try to relate prices with network structure, they say, oh, let's target the ones that have the highest degree. But what this showed that the degree is just a crude approximation of one's influence. I think a good experiment would be, suppose that I only had information on the degree, okay? I just had this first order information on the agents. Can I do better by knowing the whole structure and when I can do better? We haven't done this, but I think this would be very interesting.
It seems also from the results, from the graphs you showed for the first part, that when the gains were not huge, I mean the losses were not huge in donor network. So do you think it then?
No, I think it didn't become clear, but depending on the parameters of the model, the losses in asymmetric networks can be as much as like 95%, right? And so the idea of this centrality thing is that so the central agents are those not only that influence a lot, but are not influenced much. Okay, so if you remember the optimal prices, they had two terms that were identical except G and G transpose. So if I am an agent that influences a lot, but I'm influenced a lot from others, then I'm not central. So even if I have a high degree, high out degree, I may not be influential if I have also a high in degree. Okay, so the degree is just a crude approximation of one's influence. Okay.
So when you don't know the graph, so it means you apply a fixed price?
Yes. So yes.
Is it optimal?
Okay, so that would be another. No, it's not optimal. But it might be optimal if the graph is symmetric, right? That was the corollary. If the graph is symmetric, this is optimal.
My question was, is it optimal given that you don't know the graph? So for example, like distribute the price randomly and hope that a low price targets the guy with high degree?
Right. I believe it would be optimal because I mean, if I have no means to discriminate between agents, okay, I'll have to offer them the same thing, okay?
Yeah, well.
Yeah, so intuitively, yeah, but yeah.
It's not clear.
Yeah, we haven't proved it, but I think it should be true.
I guess we could conclude now.
Okay.
Let's take the speaker.
Thank you.